The lab we're going to do today is called the sensitivity of a balance. You should have in your comp book a page that looks like this. Notice we get a data table that says rubber stopper and penny with 3 different spots. Okay, and then this is the stuff from the book. I'm not going to read through it. You can do that on your own, but I'm going to work the lab out for you. So really, the whole point of this lab, we've learned so far in the first chapter that volume isn't always a great way to measure things. We saw that when we measured sand. We kind of have to do a lot of math and explain how we measured the volume of sand. If we would measure salt, we'd have the same problem because the salt's going to dissolve in the water. If we're dealing with a lot of things, they expand or contract when they get hot or cold. So a better way to measure things is mass. The mass also has its limitations, and the biggest limitation with mass that we're dealing with is our triple beam balance. Okay, and so we've worked a little bit with the triple beam balance. We just want to see right now, are we going to get reliable results if we measure the same thing over and over. And so we've got a rubber stopper that we're going to mass 3 times, and we've got a penny that we're going to mass 3 times, and we're going to mass them back and forth. And so that's what's going to go on your data table. So if I put the rubber stopper on there, I know it's not going to be 100 grams, so I'm not going to even start with that. We'll start with 10, 20. I think it's a little bit more than 20. Yeah, it's actually... If we get down here and look at this, it's about 20, and it's not quite to the 0.2, so I'm going to call it 20.19. Actually, this is the pointer's off a little bit, so I need to move it a little bit more. So let's try it again. Not 20.19. It's almost the 0.5, so I'm going to call it 20.48. Okay, so that's the stopper. So I'm going to take the stopper off. I'm going to move the riders over to 0 again, put the penny on, and see what we get with the penny. I know the penny's not going to be 20. Should be around a little bit more than 2. So that's just past the 2.5, a little bit less than 2.6, so I'm going to call it 2.58. So we're going to take the penny off and go back to the rubber stopper and do the same thing. I know it's 20-something. This time, for some reason, it looks like it's a little bit more than about 20.5. I'll call it 20. It's less than 1, so 20.98 is what it was that time. So we're going to put it back on 0. Put the penny on there. See what we get for the penny again. I would say this time it's about, I would say it's exactly on the 0.6, so 2.60. So we'll take the penny off and mass the stopper for the 3rd and final time. And it looks like it's about 20.98. So maybe the first time there was just an error on it. And then we'll put the penny back on for the 3rd and final time. And for the penny, we know it's 2 point something. This time I would say it's a little bit past the 0.6, so 2.62 is what will make that final measurement for the penny. So I'm going to take the penny off and then re-zero that. So that's part 1 of the experiment. Let me see if I can get this set up so you can see part 2. For part 2 of the experiment, it says to take a piece of graph paper and cut it into 20 by 20 squares. So if you take 20 times 20, that's 400. So there's 400 squares right here. And we want to know what the mass of this 400 squares of graph paper is. If you look at your book, let's go back and answer the first blue question here together. It says, does your balance give reproducible results to the nearest hundredth, the nearest thousandth, or something in between? I would say it's a little bit less than a nearest hundredth. And we're going to figure out right now exactly what it is. So this is where they talk about your graph paper. The second blue question says, what's the mass of the large square of graph paper? That's this right here. So we're going to take it, put it on the balance, and let's see if we can figure out what the mass of it is. So if I move the writer over, that's almost 1.1. I'm going to call it 1.09. So the mass of the small square of graph paper, if you can see my calculator there, I'm going to use it here in a second, is 1.09 grams. So that's going to be the answer to this second blue question. Then it says calculate the mass of a single small square. When we know that the mass of all of it is 1.09, so if we take 1.09 divided by the 400 squares there, it's going to give you the mass of a single small square. So it's 0.00, we'll just call it 0.0027 grams. So it says, for the purpose of this experiment, it will be convenient to have a group of squares with a mass between 0.003 and 0.007. So this number, 0.0027, is not between 0.003 and 0.007. So I'm just going to double it. If I take it times 2, we get 0.005, we'll round it to 0.0055 grams. And so the third blue question says, how many of your small squares are in a group that has a mass between 0.003 and 0.007? Well, we doubled it, so it's 2. And what's the mass of such a group of small squares? It's 0.0055. So that's the answer to blue question number 4. It goes on to say, now cut out 10 of these groups of small squares, and with a penny or rubber stopper already balanced, add the groups of small squares one by one, observe the effect on the balance. So we want to see when the balance moves. So let me take a second and cut out some of these small squares. I'm just going to cut out a whole line of 2s here. And let's make sure this balance is zeroed. Looks like it's a little bit above. And that's pretty close. So we're going to put the stopper on and then balance this with the stopper on it. Can't remember what it was. Almost 21, I think. Okay. A little bit less than that. There we go. So it doesn't really matter what the mass of it is. We just want to make sure that this is balanced. And you can see that the pointer here is pointing almost exactly at 0. It might be a little bit above, but we want to see at what point this moves. So I'm going to put on a few of these groups of small squares here. Well, I moved it on accident, but it should end up being the exact same spot. And it is. It looks to me like I put 4 of them on there. I saw it move a little bit, so you can see that the pointer is no longer where it was. So the question, number 5, it says, how many groups of small squares did you have to add before the balance gave you a reliable response? It was 4. So the answer to the blue question number 5 is 4. Then it says the smallest change in mass that a balance can detect in a reproducible way is called the sensitivity of the balance. So what's the sensitivity of the balance? Well, we know that each of those groups of small squares has a mass of 0.005. So if I take this times 4, I'm going to get 0.02. So the sensitivity of this balance is about 0.02 grams. So in order for me to be able to tell that 2 objects are different, they've got to be different by 0.02 grams. I would say this is a fairly sensitive balance compared to some of the other ones we've got. What we normally assume is that the sensitivity of the balance is about 0.05 grams for this. And this could just be lucky that I ended up with a fairly high sensitivity. Okay, so one of the limiting factors in mass is we don't have the same problems that we have with volume. We have a little bit different problems. Mainly, the main problem is the equipment that we use. Even if we spend a lot of money on really expensive massing equipment, we're still going to be limited by that equipment at some point. Okay?